Let's talk about Le Chatelier's principle. So the whole concept of an equilibrium, having all things present, my reactants and my products in my flask together at all times, isn't really great in the industry. If I'm trying to add two things together to make my product and then sell it, but some of the stuff I add together stays as the reactant, it's not very good for productivity, right? I want to maximize my product and convert essentially every starting reagent into my product. I want 100% yield, not just 1% yield. So here's an example of that in industry. If you're trying to make an ester through this organic reaction, alcohol and carboxylic acid make an ester and water, and I want this, remember esters are fruity smelling and sweet, and so they are your perfumes and your car air fresheners and your lip balms, and I'm trying to make like this lovely peach smelling ester or peppermint smelling lip balm, everything I put into it stays, not everything, but like a lot of it stays, and so I end up with alcohol smelling, vinegar smelling, peach stuff. Like that's, no one's gonna buy my product. So Le Chatelier played with equilibriums to see if we could get more alcohol and more carboxylic acid to convince themselves to make my ester. So that's what they're trying to do. They're trying to say like, let's shift the equilibrium so I get more products, or let's shift it back so I get less products if you want to prevent a side reaction from happening in the industry. So Le Chatelier did a whole bunch of experiments in the 1800s and found that there were three things that would shift our equilibrium. So concentration, pressure, but with pressure I have to change the volume, which then affects the pressure of the gases, and then that shifts equilibrium, and temperature. So concentration first, let's talk about concentration. So here's an equilibrium, The expression exists like this, products over reactants. I did not include the CCl4 because it's a liquid. This is a heterogeneous mixture, so I have gas, gas, gas. Include your gases and aqueuses in a heterogeneous mixture and not the other stuff. So this is not included, okay? Now the whole thing is that this is an equilibrium constant. Constant, stays the same, constant. So as soon as I play with any of these things, like for example, increase this or increase that or decrease, it's going to affect my Kc value. So let's say I make this number, let's use the top number, it's easier. Let's make this number bigger. The Kc is like, I don't want to be bigger, I want to be smaller. So it compensates and it makes this number bigger so that it can keep its ratio. Okay, so for example, if this was supposed to be 2, and at the moment it's 2/1, and then you just change this to 4, it's like, oh my gosh, I can't be 4/1, I'm supposed to be 2/1. So I better change this to 2 so that I'm 4/2, and then that's the same number 2 constant. Okay, so I use a bathtub analogy in this because a bathtub is very much like an equilibrium. I mentioned that at the very beginning, how I still have a convection current happening, but it could kind of, so if I take, but it looks the same is what I was about to say, it's still level. So if I were to increase the amount of HF in my system, the system goes like, hey, I had the perfect amount of HF and then you just added a bunch. How very dare you? And so it will shift to use it up. It's like, oh, all that extra HF I did not want, I'll use it up. So and this is the bathtub analogy here. So if I dump in a bunch of HF, it'll shift towards the products to use it up, okay? So just like the bathtub, dump in the bathtub, the bathtub's gonna slosh this way, slosh back and forth, until it reaches a level playing field again, until it reaches an equilibrium. Okay, so if I increase HF, it's gonna shift right, which is towards the products to use it up. That's what I said. And what that's gonna result in is more of this produced, more of those produced, and, oh, I forgot my little F2 in there. F2. And in order to produce more of those things, I have to use up the HF that I just added. So let's say I added, 1,000 molecules. I would use up 200 of those. So I'd still have 800 extra, but whatever, it's better than it was before. And I'm going to also have to use up some of this stuff in order to make my products happen. Okay, so increasing the HF concentration is going to shift right to use it up, which is going to result in an increase of these and a decrease of these in order to make those. Okay, so let's do the same thing. Let's scoop out of the bathtub some HCl. If I were to scoop out of the bathtub a bunch of water on this end of the bathtub, right? So here's my whole bathtub. You get that? And then I scoop this out. What happens is the water rushes to replace it. So the equilibrium goes, how very dare you? I had the perfect amount of HCl and you've just taken it away. So it rushes to replace it. So a decrease in HCl concentration shifts right to replace it. And then I get the same things happening. I get more of this produced and I have to use this up in order to produce that. Okay? So this is a good way if I'm trying to sell my HCl, as soon as I make it, I take it away. And the reaction is like, hey, I thought I just made some. I guess I'll make more. So then it makes more and then you take it away and then it's like, hey, where did all that stuff go? Guess I'll make some more. And it makes like, nice. Okay, so, but what would happen if I increased the amount of CCl4 in there? Well, nothing. Because the whole concept, the whole reason it's doing this is to maintain that beautiful, perfect equilibrium. Remember, concentration does not change equilibrium constants. So what I'm trying to do is I'm trying to maintain it. But if I change the CCl4, no CCl4 in here. And so I'm not actually changing my K value. And so it doesn't need to shift, and so it won't shift. So if I increase or decrease this liquid, these guys are like, I don't care. All right, so now let's look at pressure. Just joking. I thought that we were done. Concentration, but we're not. Here are 3 tricky concentration problems because like sloshing into the bathtub and scooping out of the bathtub is easy. So here are some weird ones, okay? So let's say we're gonna end up forming a water or a precipitate on these weird ones. So here, these are all aqueous. I have some what is this stuff? Aluminum hydroxide, and I'm making aluminum ions and hydroxide ions. So just a dissociation equation here. And I add some HCl to this reaction. And I find that the equilibrium shifts when I do this. So weird, right? Because adding HCl is like, not this bathtub. I got this stuff and this stuff and this stuff in this bathtub, not in the HCl. But when you dig a little deeper, you know that HCl contains H pluses and Cl minuses. So when I'm dumping in some HCl aqueous, I'm actually dumping in these 2 ions. Okay, so do these 2 ions have anything to do with the above equation? Well, sure they do. Because what happens is the OH minus and the H plus see each other, and the H plus takes away those OH minuses and locks them into water. And so what the equilibrium says is, hey, who took all our OH minuses, right? And the H plus is like, we did. So who took all our OH minuses? And so it has to shift to replace them. You can't probably see this marker, switch for you. So it has to shift to replace them because they just disappeared. They're no longer in this equilibrium because remember, these are all aqueous, and in order to be in the equilibrium, you have to be aqueous. All of a sudden, these are liquid. They're not even seen by this balance. And so this equilibrium is like, what? So it shifts to replace it. So increasing the HCl concentration actually decreases the OH minus concentration, and that results in a shift to the right. Okay? So a shift to the right means that I'm going to end up increasing those Al3 pluses that are there. For example, I'm going to replace some of my OH minuses, and I'm going to decrease some of my some compounds. Okay, makes sense? Let's see another one. Very similar, but looks different. So I've got some calcium carbonate dissociating into some calcium ions and carbonate ions. And I'm going to add all aqueous. So I'm going to add some sodium fluoride. And you're like, not this bathtub, right? I don't care. Shouldn't shift the equilibrium, but it does. So whenever you see something that doesn't seem to tie together, I need you to just look again. I need you to look to see if we're forming water or precipitate here. So HF, what I'm actually adding is, or NaF, I mean, what I'm actually adding is Na plus and F minus ions, right? My species list, it's a big part of Chem 30. So my species list here are these two ions. So I think to myself, do these two ions have any effect on this system? Well, I'm not going to form my water, right? There is no HOH happening here. But I am going to form a precipitate. So you need to go to your data booklet and you need to, I don't know where my data booklet is, but, and look up on that page that is the solubility table from Science 10, and you have to see if this is soluble. So you look at the negative ions. I have this negative ion and I have this negative ion. I follow the negative ions. If you find the F minus at the top column and you look down below and it says that your 2+ group 2 ions are going to form a precipitate. So these two see each other, right? They like fall in love, they react together, and they fall to the bottom of the bathtub as calcium fluoride solid. So here I get a precipitate formed. Meanwhile, the equilibrium goes, where do our calcium ions go? Oh, they fell in love with the F minus and ended up as a precipitate down at the bottom of the bathtub. Oh man, we got to replace them. So they shift the equilibrium to the right to replace these ions. It's a coincidence that those are two shifted to the right, okay? Or that everything I've done is shifted to the right so far. It's just a coincidence. You can shift it right, the other way too. Left would be the other way. Okay, so I'm shifting towards that calcium to replace that calcium, and I end up with an increase. So hold on a minute. So increasing my NaF concentration equals a decrease in the calcium ion concentration because of the formation of that equilibrium there, which would equal, okay, it's going to shift to the right, which is going to equal an increase in the calcium 2+ to replace some of those, and an increase in the carbonate ion, and a decrease in that compound. Okay, so all those three things will result. Okay, all right, one more. So if I have this reaction here, and I'm going to add some silver nitrate, I think, not this bathtub, and then I remember, oh yes, I'm supposed to think again, look at my species list, Ag+, NO3-, can't form water, but I can form a precipitate. You look at your precipitation table and you see that this calcium or chloride ion and the silver ion are going to form a precipitate of AgCl solid. So actually increasing the AgNO3 results in a decrease of my Cl- concentrations. And so the reaction will shift to the right to replace them. Okay, so this is asking about color though in this question because, hold on a minute, just need some space here. Okay, so this is asking the color, the question in your notebook is asking about color here. So first of all, it asks for what color would it be and then what color would it become. So what color would this be? Well, you could assume all four things are present, that the equilibrium is about 50-50 here. You're making that assumption based on the multiple choice answers. And so or they could give you a K value. And if the K value is close to 1, then you have a perfect mixture of both of those things. And so my original color, because it's a combination of both of those things, is purple. So I'm going to go from purple, P-U-R for purple. So I start as purple, and then if I'm shifting it to the right, I'm making more pink. So it's going to go purple to pink, or maybe to a lighter purple, or to, you have to look at the multiple choice answers and figure out exactly. But if it was a written response, purple to pink is perfect, and I would give you a K value of close to 1. Okay, so those are tricky concentration questions.